4, 5, everybody in the car, so come on, let's ride to the liquor store around the corner. The boys say they want some gin and juice, but I really don't wanna. Mambo number 5.
If you think the heat is grueling this summer, check out this proof. Every year, the International Math Olympiad, or IMO, is held. It's one of the top competitions in math. This year, the 2022 IMO presented some pretty formidable problems, one of which caught my eye. Problem number 5. It reads, find all triples, A, B, P, of positive integers with P prime, and A raised to the P power is equal to B factorial plus P. Now on the face of it, this problem seems rather straightforward. But the idea behind this type of a problem is to first find any solutions that may exist, and then prove that no other solutions will exist. And that is the subtle details in this problem. Few definitions. A to the P power is really saying that we're going to multiply the positive integer A P times with itself. B factorial is for any given number, multiply it by itself, and the number that comes before it, and the number that comes before it, all the way down to 1. So B factorial is defined to be B times B minus 1 times B minus 2, all the way down to 3 times 2 times 1. So all the numbers in between 1 and B are represented in this multiplication, this factorial. And just to cover all bases here, P is a prime number means that it is a number that is only divisible by 1 and itself. And that makes for a good number theory problem. Step 1 is going to be feeling the problem out. And typically we do this using a numerical approach. Numerical approaches make a little bit more sense initially, and they give us an idea of how the problem is going to work out in general. Numerical evaluations. So the first thing we're going to do is pick the smallest prime number that exists, and that's going to be P equals 2. So plugging in P equals 2 into our equation here, we get A squared is equal to B factorial plus 2. Now what we're going to do is we're going to treat B as the independent variable, and we're going to start plugging in some positive integer values for B to see what the result is. So we see that first, A squared is equal to 1 factorial plus 2 equals 3 is not a solution because there's no integer squared that will equal 3. And if we plug in B equals 2, we get A squared equals 2 factorial plus 2. That equals 4, which actually is a perfect square, so there is an integer that exists when squared that equals 4, and that integer is 2. So we've now found a solution to this equation, that when A is equal to 2, and P is equal to 2, and B is equal to 2, this equation is satisfied. So the solution 2, 2, 2 is our first solution. So at least a solution does exist for this equation. Now, if we examine what happens down the line here for this equation to see if any other solutions exist for P equals 2, we begin to see a pattern that emerges. At B equals 3, we have 2 cubed, and 2 cubed, although it's a perfect cube, is not a perfect square. And then every number that seems to come after B equals 4, or B equals 4 included, seems to be a single multiple of 2, our prime number. Okay, and so this will be actually a pattern we're going to find holds in many cases here, and that's going to lead us to a general case that we're going to need to prove. So it seems that if there's going to be just a single multiple of 2 for the rest of the b values, then there's no perfect square that would equal this. In other words, if I took the square root of the right-hand side, I would always be left with a factor of the square root of 2, which is an irrational number, not an integer. So no other solutions would exist if every other number after this is going to be a single multiple of 2. Let's take a look at p equals 3. So the next prime number is 3. And if we plug 3 into the equation, we get a to the third power is equal to b factorial plus 3. Now, creating a table of values, just as we did before, we let b start at 1. Since we're dealing with positive integers, b has to be starting at 1. 1, 2, 3, 4, etc. We plug in for b factorial, add 3, and see if we come up with a number that is a perfect cube, a cube. When we plug into b equals 3, we get a cubed is equal to 3 factorial plus 3, which gives us 9, and that's a perfect square. So we might be close. And of course, when we look at b equals 4, we get a cubed is equal to 4 factorial plus 3, which equals 27. And this is a perfect cube. It's equal to 3 cubed, so a is equal to 3 is another solution to our equation. So when p is equal to 3, a is equal to 3, and b is equal to 4, so the solution 3, 4, 3 is the second solution for our problem. So we're making some progress here by just testing out and feeling out the problem through some numerical analysis. Now, as in p equals 2, we see with p equals 3 that after we hit a certain b value, all the rest of the numbers that seem to come out of a cubed are a single multiple of 3, a single multiple of our prime number. What that would suggest is that if we took the cube root of both sides of the equation, we will always be left with the cube root of 3, which is not an integer. So therefore, we would not have a solution to this equation after a certain p-value here. But that's only if we can show that every number after this would be a single multiple of 3. Okay, so we can also take a look at the next biggest prime number, which would be 5, and really see if this idea is being driven home. So with p equals 5, we get the equation a to the 5th equals b factorial plus 5. And what we notice is that the first couple of values for b generate numbers that are not divisible by 5. Then at b equals 5, we get a number that is equal to 5 cubed, but we need something that's going to be an integer to the 5th power, okay? And as we progress, we start to cycle out. Each number is either a multiple of 5 squared or it's a multiple of 5, and then after a certain value, it just becomes a single multiple of 5. Now, if we look at the b values that this happens with, it turns out that if b is bigger than or equal to twice the prime number, here is 10. In the other case, 2 times 3 would have been 6. Alright, then we start getting single multiples of that prime number, which would suggest that there is no solution to the equation after a certain b value. Okay, so that's something we're going to now conjecture here, that for b greater than 2 times p, that we do not get anything divisible other than one multiple of our prime number. So 8 raised to the p power is only going to be divisible by the prime p once, not twice. So p squared would not divide a to the p power. I know this might be a little bit to chew on here, but think about divisibility and prime numbers being the numbers that are the building blocks of other numbers. So you can't break down a prime anymore, which makes it a good tool. Now we're going to test our conjecture. So our conjecture is that no solution exists when the b value is greater than twice the prime. Now we need to prove this is the case. Alright, so we start off by saying if 2p is less than or equal to b, then, well, one thing that we can say is that if 2p is an integer less than the integer b, or less than or equal to, then the number 2p will divide b factorial. And that's how we symbolize will divide with that slash in the middle. So 2p divides b factorial. Now, this has an implication. Okay, this is going to imply that p, in fact, divides b factorial, because if 2p is in a factor of b factorial, so is p. And therefore, so is p squared. So now we can argue that p squared divides b factorial. Now, if p divides b factorial, we can also imply something else, that p divides b factorial plus p. Since we know that p divides p divides b factorial, p divides the sum of those two things. And that sum is equal to, from above, a raised to the p power. So in conclusion there, we can say that the prime, p, divides a to the p power. And that implies that since we have p divides a to the p power, p also divides a. Okay, so now we know that p divides a. What else does that mean? So if p divides a, that implies that p squared would divide a squared. And since a squared is less than or equal to a raised to the p power, p squared divides a raised to the p. Now, if p squared divides a raised to the p power, then p squared will also divide a raised to the p power minus b factorial, because we know p squared from over here divides b factorial. And so since p squared divides a raised to the p, it will divide its difference. And because it divides its difference, that's also equal to prime p. If you rearrange the values of this equation up here, you can get that a to the p minus b factorial is in fact equal to the prime, and that leads to our contradiction, that p squared divides p. That's something that can never happen. A squared can never divide that number. So that's a contradiction. And so that tells us that the situation that we assumed above here, that is, this assumption right here, cannot be true. Therefore, the case must be that b is less than 2p. Now, think about this just for a moment. If we're talking about integers, and 2p is some integer, and b is a number that is less than that integer, strictly less than that, then the largest integer that b could be equal to is 1 less than 2p. So we could say that b is less than or equal to 2p minus 1. Okay, so that's the first part of our argument. That's going to give us an upper bound on b, meaning that b can never be greater than 2p minus 1. Alright, so the first leg of our race here is we created a conjecture based on our numerical analysis, and we've now proven that b cannot be greater than or equal to 2 times the prime, otherwise no solution exists. So therefore, b must, if a solution exists, which we know solutions do exist, that b is bound to be less than or equal to 2p minus 1. Now that we've established that b is less than or equal to 2p minus 1, we can write another inequality. b factorial is less than or equal to 2p minus 1 factorial. And because p is a positive number, a positive prime number, we can add it to both sides of the inequality, not changing the inequality. So b factorial plus p is less than or equal to 2p minus 1 factorial plus p. Okay, so now why would I write this inequality? Well, b factorial plus p is equal to a raised to the p power. So we can say that there is an upper bound on that, and that is that it has to be less than or equal to 2p minus 1 factorial plus p. Okay, so next we're going to explore something called the AMGM inequality. And that stands for the arithmetic mean, geometric mean inequality. This is often used in IMO problems on the number theory problems, and it states that the arithmetic mean of a set of numbers is always greater than or equal to the geometric mean of that set of numbers. So I want you to consider the set of numbers 1, 2, 3, etc., all the way up to 2p minus 1. So these are all integers, all numbers up to 2p minus 1. What would be their arithmetic mean, or their average? Well, since this sequence of numbers constitutes an arithmetic sequence, we can say that the average, or the sum of those numbers divided by the number of things that are in there, will give us the arithmetic mean. So that means that I would add up 1 plus 2 plus 3 all the way up to 2p minus 1, and I would divide by the number of elements that are in this set, which are 2p minus 1 elements. Now if I examine the above piece right here, we notice that this is an arithmetic series. In other words, that this sum has a formula that we can use to find out what it equals. Alright, so if the top sum there is equal to Sn, and again this is an arithmetic series, then it will be equal to 2p minus 1 multiplied by 2p minus 1 plus 1, which will just be 2p, all divided by 2. Okay, so that's the numerator part there, is what that is equal to. So together, our arithmetic mean is equal to 2p times 2p minus 1 divided by 2 times 2p minus 1. And of course, you can see what's going to happen here. The 2p minus 1's cancel, the 2's cancel, and we get our arithmetic mean to be equal to our prime. So let me record that here. Our arithmetic mean is equal to p. Okay, next is to find the geometric mean. Okay, and the geometric mean is going to be found by taking the, if it's two numbers, we're going to be multiplying those two numbers and then taking the square root. If it were three numbers, we'd be multiplying those three numbers together and taking the cube root. So here, we're going to be multiplying all the numbers in our setup here together, which is really just 2p minus 1 factorial. But then we're going to need to take the 2p minus 1 root of that number, which we can express as raising this to the 1 over 2p minus 1 power. So again, this character right here is indicating a root of the number that we get from 2p minus 1 factorial. Okay, so that gives us what our geometric mean is equal to. So with the AMGM inequality statement up here, we can substitute our values and say that P is greater than or equal to 2p minus 1 factorial raised to the 1 over 2p minus 1 power, which is another way of saying that p raised to the 2p minus 1 power is greater than or equal to 2p minus 1 factorial. So this gives us some ways of putting some boundaries on what the value of p can actually be. The AMGM inequality is a way of putting restrictions into number theory problems that often involve sums and products. So now it's time to employ a clever bit of mathematics using these two inequalities. Alright, so now what we can state is that b factorial plus p is less than or equal to 2p minus 1 factorial plus p, as we have stated right over here. This allows us to say that this is less than or equal to p raised to the 2p minus 1 power from the inequality we established over here. Now we're going to do a little bit of manipulation with p raised to the 2p minus 1 power. And so if we have this particular case, what that means is that this is going to be less than or equal to p raised to the 2p minus 1 power plus p. Right, if I add a positive value to that, it will be greater than or equal to that. Strictly greater than, usually. Now, what we can argue is that this is strictly less than the same thing as if we would have p raised to the 2p minus 1 power added to itself. Right, because this one up here is p to the first power, and 2p minus 1 is going to be greater than 1. So this will be strictly greater than 2p minus 1 power plus itself. And another way to write this statement right here is 2 times p raised to the 2p minus 1 power. And another way to write that would be that this is going to be less than or equal to, well, p times p to 2p minus 1 power. Since p is going to be greater than or equal to 2, and in this case we're going to assume that p is greater than 2 when we're looking for solutions outside of 2, then we're going to say that we know that p is going to be greater than 2, so that makes this inequality hold true. And another way to write this piece is just p raised to the 2p power. Alright, so let's put that all together. So we have that b factorial plus p is strictly less than p raised to the 2p power. So now we need to explore, what does this piece mean to us? We're now going to explore the implications of this inequality because there's something in here that's subtle. You see, the left-hand side of this inequality is actually a raised to the p power. So we can say that that's strictly less than p raised to the 2p power. And that could also be written as p squared raised to the p power. So we can say that a raised to the p power is less than p squared raised to the p power, which implies that a is less than p squared. So a is less than p times p. Let's make a equal to some multiple of p where that multiple is less than p. So that makes this inequality right here hold true. Okay, so now we have k is less than p, and we're going to assume that k is not equal to 1. If there exists some number q such that it divides a, which is equal to k times p, and let's suppose that q is a prime, so if there is some prime that exists that divides a, then that implies that q is less than that prime. So the prime q is less than the prime p. But now that means that q does not divide p, since p is a prime, and is only divisible by 1 in itself. So therefore, that implies that since q does not divide p, q does not divide b factorial. And thus, q must be greater than b. So where are we going with this? Well, if the prime p is less than or equal to a, that would imply that the prime p is less than or equal to b. And by definition, p less than or equal to b would have to be less than or equal to q from our statement over here. And that's our contradiction, because then that states that p is strictly less than q. And why is that a contradiction? Well, because we said that before q is less than p, and now we have that p is less than q. So we've reached another contradiction. And that contradiction tells us that our assumption that k was not equal to 1 is false. So therefore, k must be equal to 1, which implies that a is equal to p. We have now proven that the number a must be equal to the prime p. So the natural question then arises, why does the prime p have to be less than or equal to a or b? In other words, is it possible for the prime p to be greater than a or b? We're going to break this down into a few cases. Alright, so case 1 is going to be, we're going to assume that a is less than or equal to b, which is strictly less than p, which means a is strictly less than p. Alright, so what does that assumption lead us to? Well, first we can say the following. If a is less than or equal to b, then a divides b factorial. That would also imply that a divides a raised to the p minus b factorial, and that's equal to p. So that implies that a divides p. Since p is a prime and has no other divisors besides 1 and itself p, then we have really two cases to consider in this case. So we have, first, if a is equal to 1. Right, so what does this statement again mean? It means that either a is equal to 1 and divides p because of that, or a is equal to p and divides p because of that. P is a prime number, so those are the only two possibilities. So if a is equal to 1, then the equation a to the p power equals b factorial plus p then becomes the equation 1 to the p power equals b factorial plus p, or 1 is equal to b factorial plus p. Now if we take the prime p and subtract it to the other side of this equation, we get that b factorial is equal to 1 minus a positive number that's bigger than 1. So that means that the left-hand side of this equation right here will always be negative. And the b factorial, since b is a positive integer, will always be positive. So the right-hand side is always positive. So this leads to a contradiction, which is often indicated by two arrows pointing at each other. A contradiction exists here. So therefore, a cannot be equal to 1. Okay, so then we have to consider the case, what if a is equal to p? Okay, so if a is equal to p, well, that automatically will contradict our assumption here. So both cases fail. Therefore, this statement right here is false. So that can't happen. All right, so let's make a little list of the cases that we've ruled out. Case 1 is the case a is less than or equal to b, which is less than p. And that case does not work. All right, so now we'll consider another case. All right, case 2. We're going to assume that, well, since we assume that a less than or equal to b is less than prime, all right, we can maybe strengthen that case by just showing that if a is exactly equal to b less than p, that is again something that would lead to a contradiction. All right, so this is really, we could have maybe stated the first case as strictly less than, right? But here we're going to show that equal to cannot happen. Okay, so here, if a is equal to b, then we have a raised to the p power is b factorial plus p, or we can rearrange this a little bit and say that a to the p power minus p is equal to b factorial. So we know a little bit how powers of exponents and factorials are related to each other, so we're going to make a few observations. Let's observe that a factorial is less than or equal to a raised to the a power. And since a is equal to b, we can say that that's the same as saying that it is less than or equal to a to the b power. And since b is strictly less than p, we can say that this is strictly less than a raised to the p power, which is equal to b factorial plus p. Okay, so now p is a positive value, so a factorial minus p will have to be strictly less than a to the p minus p. Okay, and that is going to help us because this is equal to b factorial. So this says to us that a factorial minus p is strictly less than b factorial. And if I rearrange this equation just a little bit, it says that a factorial minus b factorial is strictly less than our prime. Now we know that our prime has to be greater than 0, so we can state that this is greater than 0. And a and b are both positive integers. And we've assumed here that a and b are equal to each other. So therefore, if we have that here 0 is greater than a factorial minus b factorial, that implies that b factorial factorial is less than a factorial. And that implies that b is less than a, right? And b less than a is in fact a contradiction to the fact that a was stated to be equal b. So this is another case of contradiction, just to show that a cannot be equal to b. In the case of, we're investigating here, remember that b is going to be, the prime p is going to be greater than, well, here, we already investigated cases of both 2 and 3 as primes, so our cases here are going to be p greater than or equal to 5. Alright, so for p greater than or equal to 5, that means that this is a contradiction. Okay, because that would imply then that a is not equal to b. Alright, so case 2, if we can call it case 2, it's really just to show that a equals b less than p is not possible. Alright, so we've ruled out that case. Case number 3 would be to assume that b is strictly less than a, and that's strictly less than the prime p. Alright, so both a and b are strictly less than p. In other words, that both the prime is greater than both a and b. Alright, and that's really kind of driving home this question that we had posed over here, which was that is it possible for p to be greater than a or b? So now, how does this one work? Well, if a raised to the p power is equal to b factorial plus p, what can we say about this if we know something about b factorial? So we know b factorial is the least member of a, b, and p here. So b factorial, let's just write this out here, we know is less than or equal to b raised to the b power. And that's going to be strictly less than b raised to the a power, which is strictly less than b raised to the p power. And since b is less than a, this is strictly less than a raised to the p power, which is equal to b factorial plus p. Now, since a and b are, again, integers, and positive integers at that, we can call them natural numbers, and b is less than a, okay, keep that in mind right there, all right, then we should be able to write a as b plus 1. In other words, a we can assume is 1 greater. What happens when a is 1 greater than b? All right, so we're going to investigate that now. Okay, so we're going to observe that b factorial, which is less than b raised to the p power, would have to be less than b plus 1 to the p power minus p. Again, a to the p minus p is equal to b factorial, so making the substitution of a equals b plus 1 right here, okay, we're going to investigate what that's going to look like. Now, if we use the binomial theorem to expand out b plus 1 raised to the p power, it's going to be something like this. It's going to be b raised to the p power plus a whole bunch of positive terms in the middle here, plus p times b plus 1, and then we'll have a minus p on the end of that. So one can definitely argue that all of the pieces being added on here are bigger than 1, greater than 1. Alright, so that means that this piece right here is definitely going to be bigger than this piece right here. So we've established that b factorial is less than b to the p power, which is less than b plus 1 to the p power minus p, which would be equal to b factorial given our equation. So that's a contradiction right there, because that says that b factorial is strictly less than b factorial. So that is a contradiction. Therefore, this case right here is not possible. So now we've explored all possible cases here. For A or B to have P greater than them. So we have all cases showing us that A and B cannot be less than P, right? That this case doesn't hold, and so therefore we are showing that P must be less than or equal to A or B. Okay, we're going to make a few observations here. One, if we were to have some other prime, let's say Q is a prime, such that, alright, that this prime is less than or equal to B, and this Q divides A. Right. Well, then that would have to imply that Q is equal to P. In other words, that Q is that prime. You see, this would imply if Q divides A, then Q has to be less than or equal to A. And Q is less than or equal to B. Right? So if we already knew that P must be less than or equal to both A and B, then we want to make the case that we're here at P is greater than A, greater than or equal to A, which is greater than or equal to B. So before we go any further, the question might be, could A be the one that's greater than or equal to B? In other words, can we have the prime B be less than or equal to A? So one might ask the question, could it be that A is greater than or equal to B? In other words, can we have P less than or equal to B, less than or equal to A? Well, first, we've established that A is equal to P. So that would mean that P must be equal to B, which would be then equal to A. We know that that's true for the solution 2, 2, 2, but we have another solution 3, 4, 3 for A, B, and P. So that suggests that A is equal to P, but that B is greater than both A and P. So in this case, we have a solution that B is in fact greater than A. So that has to be true. So therefore, we can rule out this case right here. Next, we observe that since A is equal to P, which would maybe imply that we just need to think about this case, we have A to the P power minus P is equal to B factorial. So then this becomes P raised to the P power minus P is equal to B factorial. So now we have to explore what this implication means. We can show that P raised to the P power minus P could be factored as P times P raised to the P minus 1 factor minus 1. In other words, we can pull a factor of P out of that binomial. Furthermore, we could factor that into P times P minus 1 times P raised to the P minus 2, etc., all the way down to 1 in a geometric progression. Well, that's going to be much greater than if we just had p times p minus 1 times just the first term in that series, p raised to the p minus 2. In other words, if we consider just multiplying these two terms and just the one term here, that's going to be greater than if we were to add more terms on, which is what we have here. Greater than or equal to p factorial, which if you remember is p times p minus 1 times p minus 2 all the way down to 3 times 2 times 1. So all of the characters p minus 2 all the way down to 3, 2, 1 is going to be less than p raised to the p squared minus 2 power. Alright, so now we've established this important inequality that states that p raised to the p power minus p is strictly greater than p factorial, which is another way of saying b factorial is greater than p factorial from our statement above here. Well, that just tells me that b is greater than p. Which then would have to imply that b is greater than a. And so, since a is equal to p, remember from this statement over here, that's where we have the situation where now we have an ordering to our variables, our a, b, and our p. So we can state that both p, which is equal to a, has to be less than or equal to p. Excuse me. So we first have p is less than or equal to b. And we know that b must be less than or equal to 2p minus 1. Alright, so this particular ordering right here has now locked in the values of b for all possible values of b, and we remember for this case that a is always equal to p. So these are the solutions that exist. Right? So what we're doing is that together with both 1 and 2 here, what we have finally established is that p is the only prime that is less than b and divides a. Now, you might not be convinced that there are no solutions for b equal to p when p is greater than or equal to 5. It just appeared that way, but then we showed that if b is greater than twice p, then there's no solutions. But what about if b is equal to p? We know that there is one solution for which this holds. P equals 2. We get the solution 2, 2, 2. A is equal to B is equal to P, which is equal to 2. But you might not be convinced that there are no other solutions for B is equal to P. So what I want to show here is I want to show that B cannot be equal to P for when P gets greater than or equal to 5. So 5 or greater than the prime is never equal to B. Okay, so let's show this. And how are we going to do this? Well, we're going to do something called a proof by induction. And proof by induction usually involves 3 cases. The first case is usually the initial case. The second part to this is the assumption, which you assume something is going to hold true. And the third part of the induction is usually called the induction step, which is to show that the next case holds true, which proves that any arbitrary case holds true. So that's the basic assumption, these basic ideas behind proof by induction. Okay, so what are we trying to prove here? Okay, well, we want to show that P is not equal to B when P is greater than or equal to 5. In other words, we want to prove that P raised to the P power minus P is always greater than P factorial for P greater than or equal to 5. Because remember that this thing right here is equal to B factorial. Okay, so we're basically going to be showing that B must be strictly greater than P. Okay, that's what we want to show. B is not going to be equal to P. It must be greater than P, because we know in our boundaries B must live within these boundaries up here. So then we're trying to prove that B cannot be equal to P when P is greater than 5. Okay, so how do we do that? The first case, or case 1, is to show that the base case holds, the initial case. So the initial case would be for P equals 5. Alright, so we're going to show that P to the P minus P is greater than P factorial when P is equal to 5. Okay, so 5 to the 5th power minus 5 greater than 5 factorial. Well, in fact, if you calculate this number right here, it's the number 3120. And that is definitely going to be greater than the number that this is equal to, which is 120. So we can show that our base case holds true. Next, case 2. Case 2 is to assume that this pattern will continue up to a certain integer value. So we suppose that for some integer value k, where k is going to be greater than 5, because we've shown for equals 5 it works, we're going to say, suppose that for some value out there greater than 5, that this relationship holds true. Now, to show that k to the k power minus k is greater than k factorial, it is actually sufficient enough for us to show that k to the k power is going to be greater than k factorial. Alright, so that's what we're going to set out to prove here. Okay, so our assumption is that this holds true for the value of k greater than 5. Okay, so we say that this assumption holds or is assumed to be true. The third part to this would be then, I shouldn't call these cases, they're more like parts, but part 3 or case 3 is to show that if this inequality holds for the kth integer, that it holds true. We want to show that this holds true for the k plus 1th integer. In other words, the next biggest number. Alright, so what we do is we look at the form of this inequality and we plug in k plus 1. So that's going to say we want to show that k plus 1 raised to the k plus 1 power is greater than k plus 1 factorial. Now, this type of proof by induction is not a beginner proof by induction. This is a little bit more advanced, but follow with me if you can, because this one is not that difficult. Okay, so the first thing I'm going to do is I'm going to factor out a k plus 1 from both sides of this equation. So a k plus 1 factored out of this side, and a k plus 1 factored out of this side. That'll leave us with k plus 1 to the kth power here, and k factorial here. We can cancel these terms out of the inequality and focus on the case k plus 1 to the kth power is greater than k factorial. One can definitely logically argue that an integer greater than k raised to the k power is going to be greater than k raised to the k power, and by our assumption, this is greater than k factorial. So this is also by assumption. So it's using this case right here to strengthen our argument. Then, because of the transitivity property, we can state that, cutting out the middleman here, that k plus 1 to the kth power is greater than k factorial, which proves that it holds for any arbitrary case for k greater than 5. So by our assumption, we have finished our proof here to show that, in fact, we have b must be greater than p. B cannot be equal to p. So now we're going to take a slightly deeper dive into the concept of divisibility. And for this, we're going to use a tool from modular arithmetic. So bear with me, we're almost there, but we have to cover a few more things. So now, if we have b is strictly greater than p, then let's let p plus 1 be the smallest element that b could be equal to. Right? Maybe I should have written the inequality initially like this. Okay, so to make sure, whatever integer might be the integer that is the least number less than b, since we know if b is strictly greater than the prime, in other words, we know that the inequality above here really would be strictly greater than p, okay, then what happens is, if we have the next, the smallest number in that set to be greater than or equal, for b to be greater than or equal to the smallest element in that set. Okay, what happens then? Well, if this is the case, then we can say that p plus 1 will divide b factorial, because p plus 1 would be a number less than b. It will be one of the factors of b factorial. Also, given p plus 1 is an even number, because p is always an odd number for p is always an odd number greater than 2. So we know that p plus 1 is an even number. We would know that p plus 1 divided by 2 would result in an integer. Dividing an even number by 2 is still going to give you an integer. So this particular integer will also be something that divides b factorial. So we can say p plus 1 over 2 divides b factorial. It's also worth noting that 2 divides b factorial, because 2 is one of the factors of b factorial. Alright, so this is now going to lay some groundwork for us to talk about divisibility. So now, if we have p plus 1 over 2 divides b factorial, 2 divides b factorial, and p plus 1 divides b factorial, then we can make the statement that 2 multiplies by p plus 1 over 2 multiplied by p plus 1. We would like to ask the question, does this in fact divide b factorial? In other words, we have all of these different things that are divisors of b factorial, but what we're asking is if we multiply all of them together, is that also a divisor of b factorial? Okay, so if I were to look at the statement right here, what we're asking is really, does p plus 1 squared divide b factorial? Alright, so that's going to be the thing that we're going to investigate here in our deeper dive here. So now we are investigating this question right here, and if we have the case where p raised to the p minus p is equal to b factorial, because remember that a is equal to p, alright, then we must determine if p plus 1 squared divides p to the p power minus p. So now this becomes our new question. Is this possible? So we're going to make a few arguments involving p raised to the p minus p. Observe. P raised to the p minus p is equal to p times p raised to the p minus 1 minus 1. We can factor out a p from that expression. So if we were to ask the question whether p plus 1 squared divides p raised to the p minus p, we're really asking the question, does p plus 1 squared divide p times p raised to the p minus 1 minus 1? Something worth noting here is that the numbers p and p plus 1 are co-prime to each other. In other words, they have no common divisors. Another way you might state this is that the greatest common divisor of p and p plus 1 is 1. Alright, so that's not going to contribute to our question of the divisibility here. So we can factor the p out of this question and just ask, does p plus 1 squared divide p raised to the p minus 1 minus 1 part of this equation, about this expression? Alright, so now a few other things that we can consider here is how big p raised to the p minus 1 minus 1 is by thinking about factoring it as the difference of two perfect squares. You see, p minus 1 is going to be an even number. This number right here is going to be an even number. So this thing right here is always going to be the difference of two perfect squares. Alright, so you could factor it as that.
Whoa, this is heavy. There's that word again, heavy. Why are things so heavy in the future? Is there a problem with the Earth's gravitational pull? What?
So now we reduce the question down to, does p plus 1 squared divide p raised to the p minus 1 power minus 1? Okay, so this is a bit tricky here, but let's take a closer look at how p raised to the p minus 1 p factored. So initially we factored out a factor of p, and that gave us this. And we knew that p did not contribute to our division question, but what about if we could break down this piece here? Okay, so that's really what we're asking here. So what does p to the p minus 1 minus 1 break down into? All right. So one can show that this actually can be broken down into p squared minus 1 times p raised to the p minus 3 plus a whole bunch of even terms plus 1 there. Alright, so this factorization means that p raised to the p power minus p could be written as p times p squared minus 1 times p to the p minus 3 plus all the terms in the middle there, p squared plus 1. And so the question now is reduced to, does p plus 1 squared divide p squared minus 1 and p to the p minus 3 plus all the terms in there plus p squared plus 1. P squared minus 1 is a difference of two squares itself, so it can be factored into p plus 1 and p minus 1. So the question now is changed to, does p plus 1 squared divide p plus 1 times p minus 1 times that geometric progression of even powers. We can cancel out one factor of p plus 1 from both sides of this division and write the equation or the question as, does p plus 1 divide p minus 1 times p to the p minus 3 plus all these terms plus 1. Okay, this is where it's going to get a little bit trickier.
Never tell me the odds.
Time to break out our power tool of modular arithmetic. Time to get modular. So modular arithmetic is sometimes known as clock math. And so you think about divisibility as being the hours of the day. If there are 12 hours on a clock, then you're not going to talk about 13 o'clock or 14 o'clock. It's going to recycle back to 1, 2, etc. So this is what it's going to be here for us. The tool that's going to be put to work here is that a prime p will always be, when modulo p plus 1, congruent to negative 1. That is, that the prime p will always be 1 less than p plus 1. So anytime you do some sort of divisibility, you're going to get remainders. So if I were to divide something by p plus 1, all the remainders that would be possible for me to get would be all the numbers from 1, 2, 3, all the way up to p. Those would be all the possible remainders that I could get by dividing something by p plus 1. So since p plus 1 is the divisor, p is 1 less than that divisor, we would say that p modulo p plus 1 is congruent to negative 1. The second thing that we're going to also then state is that in this modular arithmetic here, we might be interested in knowing what p squared is equal to mod p plus 1. And that would just amount to taking the negative 1 here and squaring it, and that's going to be equal to positive 1. So p squared modulo p plus 1 is always going to be 1. Another way to say that is that if I were to take p squared and divide it by p plus 1, the remainder is always going to be 1. And another way to say that is that p plus 1 does not divide p squared. Alright, but I'm going to erase that fact for now. We'll keep these facts in mind right here. So recall in our investigation, we began asking the question, does p plus 1 squared divide p raised to the p power minus p? And we've reduced that down to the question, does p plus 1 divide p minus 1 times p raised to the p minus 3 plus all these even powers of p plus 1. Okay, so that's now our question. We've just determined what some division by p plus 1 would indicate when prime and prime squared are considered. Okay, so now a couple of other things that we might ask are, what is the value of p raised to the p minus 3 plus all the even powers plus 1 mod p plus 1? In other words, what is this thing upon the division of p plus 1. Okay, so what is that congruent to? Well, the first thing that we can notice is that since this is a sum of even powers of p, this could be broken down individually. So we have p raised to the p minus 3 power mod p plus 1, excuse me, plus all the numbers in there, p squared mod p plus 1 plus 1 mod p plus 1, and we're asking what is this congruent to? Well, all even powers of p will follow this example right up here, and so all of them will be congruent to 1 modulo p plus 1. Another way to say that is by dividing all of each of those individual things by p plus 1, the remainder would be equal to 1. So, 1 plus 1 plus 1, all the way down, all of them will be equal to 1. So, how many things are there? Well, it's easy to check that the number of terms in that expanded polynomial is p minus 1 over 2 number of terms. So that would tell us that all of these things add up to, there are p minus 1 over 2 number of terms there, so there's p minus 1 over 2 is the sum of those ones. All those ones add up to p minus 1 over 2. So p minus 1 over 2, when divided out by p plus 1, is congruent to, well, what is p minus 1 over 2 mod p plus 1 congruent to? That's a very important question to ask, right? Well, p minus 1 over 2 mod p plus 1 would have to equal p minus 1 over 2. Therefore, we can make the statement that all of these terms in here are congruent to p minus 1 over 2 mod p plus 1. So, what does that mean? Consider a number line. I'll place 0 right here. Alright, and I'll place our prime p somewhere up here, and the number that would come right after that is p plus 1. So p plus 1 sits right about there. Now, halfway between 0 and p plus 1 will be the value p plus 1 divided by 2. And I would like to argue that the number that is right before that is p minus 1 divided by 2. Right, so to show that that number, these two numbers right here are adjacent to each other, that would mean that they're right next to each other. I simply have to show that the difference of those two numbers is equal to 1. So if I take p plus 1 over 2, and I subtract p minus 1 over 2, that gives us p plus 1 minus p plus 1 all over 2, or 2 over 2, which equals 1. So we've shown that the difference between those two numbers is in fact 1, making them adjacent numbers. Now, what does that tell us? Okay, well, let's think about modular again, right? So we're doing mod p plus 1, okay? So if we said before that p minus 1 over 2 modulo p plus 1 was equivalent to 2p minus 1 over 2, that's because p minus 1 over 2 is less than p plus 1, and therefore would be one of the remainders that could occur upon dividing by p plus 1. Okay. We could also then ask the question, what is p minus 1 over 2 modulo p plus 1 over 2? Okay. Now, that p plus 1 over 2 is greater, in fact 1 greater than p minus 1 over 2, that would mean that the remainder upon dividing by p plus 1 over 2 is still going to be p minus 1 over 2. Recall from earlier we said that p minus 1 over 2 mod p plus 1 was p minus 1 over 2, which we said was equal to what p raised to the p minus 3 plus all those even terms plus 1 mod p plus 1 was equal to. So therefore, we can state that this is also congruent to this modulo p plus 1 over 2. And this is going to be the big draw here of using the modular arithmetic. Okay? So now, our question was reduced down to, does p plus 1 divide p minus 1 times p raised to the p minus 3 plus all those terms plus 1? And we can argue that this is in fact equal to the same question if I divided both sides of this equation by 2. What are each of these individual elements going to have as a remainder upon dividing by p plus 1 over 2? And we've shown that in both cases, they're going to be congruent to p minus 1 over 2 and p minus 1 over 2 modulo p plus 1 over 2. And here's the most important piece of since p minus 1 over 2 and p plus 1 over 2 are adjacent numbers, and in fact p minus 1 over 2 is 1 less exactly than p plus 1 over 2, then we can say that p minus 1 over 2 modulo p plus 1 over 2 is congruent to negative 1. And when we have two of these multiplied together, this is going to be negative 1 squared modulo p plus 1 over 2. And that's going to be equal to 1 modulo p plus 1 over 2. In short, that means that our division question, the answer to that division question is that no, meaning that the remainder upon dividing p plus 1 squared into p raised to the p minus p will be in fact a remainder of 1, which simply says that it does not evenly divide. Okay, so we have proven that p plus 1 squared does not divide p raised to the p power minus p, which is equal to b factorial for p greater than or equal to 5. Now you might not realize it, but that is the icing on the cake. In fact, we have proven now that no solution to the equation p raised to the p minus p equals b factorial exists. No solution exists for p greater than or equal to 5. And that seals the deal. We have covered every possible case for what solutions can and cannot exist. So now let's take a concept map look at what we've done. Okay, here's a complete concept map of what we've done to solve this problem. A raised to the p power equals b factorial plus p when a, b, and p are positive integers and p is in fact a prime. We started out first doing a numerical investigation of the first few prime numbers p to see what kind of an equation comes out of it and what is possible. From doing that, we found that two solutions existed. ABP is equal to 2, 2, 2, and 3, 4, 3 equals the second solution. The rest of the problem entails our proof showing that these are the only solutions that can exist. Now, we got this idea that these are the only solutions that exist by numerically investigating the values of the equation when p is greater than or equal to 5, and it did not appear that any of them had any solutions. We in fact made a conjecture that when b became greater than or equal to 2 times the prime, that no solution could possibly exist, and we confirmed that that was true. So we gave ourselves an upper bound for what the value of b could be equal to. Now, using what's called the AMGM inequality, we were able to put some restrictions on the value of the prime p in reference to p minus 1 factorial. This is a very common strategy used in number theory problems in the IMO. We were able to establish that the prime p had to be equal to a, and we ruled out any cases for where the prime was going to be bigger than a or b. So then it was just down to show that p is the only prime that would be less than b that also divides a. The last part of that is that since a is equal to p, we had to satisfy the equation p raised to the p power minus p is equal to b factorial. And we had to argue that whenever this happens, whenever the case is that p is greater than or equal to 5, that there is no solution possible for that part of the equation. So we've exhausted all the possibilities here, and we have come down to the fact that this right here are the only 2 solutions to our problem. This one was a tough one, and certainly we went down the rabbit hole on this one. This one really demonstrates what mathematical rigor is all about, leaving no stone unturned and covering all of your bases to prove beyond a shadow of a doubt that you have the answer. Thanks for joining me. I hope you'll join me on the next one. Please hit the subscribe, like, and the notification bell for more videos.